Welcome back to another video. It is Patrick from Databytez, and we are back on the technical aspects of data with the measures of dispersions, the friends whose name you can't remember. Why do I say that? Well, with the measures of central tendency, I feel like everyone, textbooks, forums, blogs, whatever, they always are quick to say, like, you need to look at the measures of central tendency. And that's because they're kind of the base descriptors that you use often. And again, we cover the measures of central tendency in another video. It'll be linked in the what you're watching. But with the measures of dispersion, they're not really as labeled. But again, you encounter them all the time as you dive into the world of data. But so the question is, what are the measures of dispersion? Sorry, see, even my mind wants to say measures of central tendency because they're just more popular. Well, those are the variance, which is sigma squared or s squared. And these are the average of the squared differences from the mean. The standard deviation, the square root of the variance, providing a measure in comparable units to the dataset. Namely, we're no longer dealing with squared units. As you can see from the squared and the variance, we are now moving to unsquared units, which allows for something very relatively comparable. And then we have the range, the difference between the maximum and the minimum values in a dataset. Now, there are a few more measures to the measure of dispersion, but these are kind of the main three. These are the other rock stars besides mean, median, and mode that we dealt with the measures of central tendency. Now, you might wonder why we have the sigma and the s. Well, that is because when dealing with the measures of dispersion, sigma comes in two flavors: known and unknown population. And these are denoted by two different equations. When the population is known, you use sigma. When the population is unknown, you use s. Why? Some mathematician thought it was better to use the s because sample s makes sense. And so we also end up replacing another character here in the formula. If you notice here, we get rid of the mu on the known population equation and replace it with x bar. Now, more often than not, you are going to be using the unknown population. And something you'll see on the unknown is that in the denominator, we are subtracting 1. And you might be asking yourself, why are we subtracting 1? Well, the reason is because whenever you're dealing with samples, you are dealing with a subset, right? You're picking a little bit of the whole to hopefully get something that's representative of the whole. But unfortunately, it'll never be completely one-to-one. You'll never have a sample or a series of samples that is without bias to some degree. And so the subtraction of 1 is to eliminate this bias. And this adjustment is known as Bessel's correction. For those nerds out there like me who like to know all the extra little ins and outs in here. Now, what do you think I'm going to say? That we need to calculate this by hand? Of course not. We are going to let the machines do the math because the machines are a lot better than us when it comes to doing things that are already known. When it comes to discovering new things, machines aren't as good, but this math is established and been around for a long time. Machines are way better at it. So let us visit another example here. Now, if you've been watching this example looks very similar, except it's been built upon. And so let me zoom out a little bit here. So we did the histogram to uncover the distribution of the dataset, which again, we are dealing with a sequence of yields. Now, what it's yielding, you can pretend it could be popcorn, candy, cars, whatever. It's some make-believe factory, but it has different sequential runs, and in each time yields a different amount. Now, we had the measures of central tendency last time. Those are unchanged, but we need to now compute the measures of dispersion. And I feel I did a little bit of a disservice covering these equations. Now, going back to our variance equation here, which I have it written out here. And again, the only difference between, this is a population known, the only difference is we would have the -1 if we were dealing with a sample. But what is mu? Mu is the average. X bar, let us revisit this equation. X bar is the equivalent to mu in the sample. So it is again just the average, where n, capital N, is the number of observations. This capital sigma, let me see if I can get my mouse over here. This capital sigma just means to sum all of them. And this I just means we start with the initial observation. The first one, the first observation that we see. And x of I is any given particular observation. So we start with observation 1 minus the mean, square it, and divide it by the total number of observations. And we do this across all observations one at a time, which is why this is called the sum of the difference of squares. And when you put it over the number of observations, it becomes the average of the sum of difference of squares. So going back to our Excel here, we understand that what we need to do. We need to take each observation, subtract the average, square it, and then divide it by the total number of observations. Now, I've already done this with an equation here, or a function, a formula in Excel, and it kind of reads like English, at least I hope so. So we have here, I'm not going to, don't get so bogged down by the details, look more so what the words mean. So we have the mean, which is this 999.9992, our total observations, which is again 10,000. We have 10,000 sequential runs. The sum of squares. So we add, going by row in this array, where you can picture each value coming in. So I of 1 is the 536 minus the mean, N4, squared. And you know what? Let's write here mean. So I minus the mean squared. It's all added together, so we get a final value, and we divide that by the observations. That is how we get a variance of 121,909.23. Now, while these yields are dimensionless here, if we had a dimension, for instance, cars, it would be 121,909.23 cars squared. Now, what in the world does cars squared mean? That is where the variance fails, because it doesn't really mean anything. We can't compare it. So we square root it. So here we have a function calling square root of this here, of the variance, and we get 349.16. Then we could just say it's 349. So now we have a standard deviation of 349 cars, which is something we can actually use. And of course the range, which is just the max minus the minimum, the highest and lowest values, meaning there is a range of 2,306 cars that are produced in yield. That is the highest range in between. So if you recall our discussion on distributions, that the normal distribution has certain properties known as the empirical rule, meaning from the average of 1,000, we can just say 1,000 cars, right? In the average of 1,000 cars, if we move 350, so let's just put here 1,000. Whoop. We have 1,000. If we go plus 350, and minus 350, so between 1350 and 650, that covers 68% of the possible distribution of outcomes from this factory to yield whatever. yield the cars. If we were to do 2, means we add it twice and subtract it twice. Then between 300 and 1700 covers 95%? Yeah. And so you can see why these measures of dispersion are important. They're all part of the same kind of initial exploration that you'll do. Something of a broader topic called exploratory data analysis. Whenever you get a new data set, you're going to want to go through a couple of steps to kind of explore and figure out what's going on. And understanding a data set's distribution, its measures of central tendency, and measures of dispersion are all important in really getting a holistic picture of what's going on with your data. And the next step would be looking at things like relationships, correlation relationships, seeing how things move with each other. If you have multiple features in a data set, which you usually will, because most data sets are not just 2 dimensions, they're multi-dimensional, sometimes 3-dimensional, which is very exciting. But this is the groundwork. This is something that will repeat over and over again as you look at data to analyze. So if you're very much inclined to learn more about data sets, this is very important. And there is a way, and I'll cover this in a video, to kind of, if you're intimidated by the formulas you see here, which we will cover in due time. We're going to figure out how to make Excel work, how it likes to work. And this will no longer elude you if you're not used to seeing functions written this way. You can do this all with the click of a button. So stay tuned if you really want to learn how to avoid writing all this. But don't be intimidated, because if you keep watching, this will be absolutely a cakewalk for you. And if you work in an office, or you have any intention to work in an office, or you just want to show off when you're working with projects with your friend, you're really going to see what Excel can really do. And it's actually quite cool. And as you progress, you'll find that a lot of the things you learn how to do in Excel carry on surprisingly to other programming languages. Namely, if you're in the data world, Python is your bread and butter. And you'll see that these concepts bleed over, so it's good to invest in knowledge in Excel. But we're getting a little bit out of topic here. The point is that we cover the measures of dispersion. You get to see why you need to take why they're important, especially as you round out your analysis of a data set's distribution. Because again, most things are normal, and most, as we covered in the distributions video. And so you're going to need variance and you're going to need standard deviation as a result to kind of figure this stuff out. Anyways, that's all for today. It's been Patrick from Databytez. My pleasure as always to bring you data related content. I hope you have a great rest of your day. Bye.